Hi everyone, I hope you can hear me quite okay. There should be a chat function and a question function if there are any issues, so please let us know if you cannot hear me okay. You can also, in dire circumstances, if you need to tweet at me if something goes wrong with your stream, you can tweet at Sarah Webb Science. But we'll wait a couple of more seconds while everyone joins in to the waiting room. Okay. All right, so thank you everyone for joining. I hope you guys are surviving your lockdown okay. Only a couple more weeks to go now, I think. But I think this is a perfect way to start off our Friday night with learning some fun science facts. And we're really lucky. We're getting a very special talk from Professor Matthew Bales. So for those of you who don't know, Professor Bales was actually the founding father of the CAS Centre, so the Centre for Astrophysics and Supercomputing here at Swinburne in 1998. And his work mainly focuses on the most extreme type of stellar systems that you can think of, so neutron stars, black holes, things that are sometimes so extreme to think about that it's hard to know, it's hard to really accept that they exist out in the universe, because they are very, very cool. And what Professor Bales uses them for is actually to test general relativity. So if you're a fan of our man Einstein down here, Einstein's famous theory of general relativity has pretty much stood the test of time, over 100 years old now, and every test that we throw at it, it seems to stand solid. So is it really the brilliant theory that does explain the universe? And it's looking like it is going to be, but that is what Professor Bales aims to figure out using these systems. So before we start, I would like to give a quick acknowledgement of country. So Swinburne is built on the land of the Wurundjeri people of the East Kulin Nation, and they are the traditional owners of the land that our Swinburne campus here in Hawthorn is built on. So even though we're not there, we would still like to pay our respects to their elders past, present and emerging. So I'm going to hand it back over to Matthew now, and he's going to give us an excellent talk. So if you, again, any issues, please pop it in the comments or in the questions, and we look forward to hearing your great questions at the end.
Okay, Sarah, can you hear me?
I can. So if you'd like to share your screen, there we go.
Sure. Right, you should be able to see an OzGrav banner. How are we looking?
Just send that live now. And just one more thing before you start. Sorry, Matthew. I'll be turning on the live captions as well. So anyone who needs those closed captions, please, you should be able to see them at the bottom of the screen. And I'll be investigating the Q&A situation, but if you do have any questions, please, for the moment, tweet them at either Matthew Bales or myself, Sarah Webb Science, and I will investigate why that button hasn't occurred. But until then, let's learn some wonderful science. So all over to you, Matthew.
Thanks, Sarah. Well, it's a pleasure to be giving this talk. I wish it could be in person, but it's good to be able to use the technology to reach out to those of you who are distributed around Australia and are interested in space. So I'm the director of the ARC Centre of Excellence for Gravitational Wave Discovery, and I'm also a professor of physics at Swinburne University of Technology in Hawthorn. And today I'm going to be telling you about gravity and neutron stars and black holes and these amazing things that make up the universe. And the title of my talk is Exploring Einstein's Universe with Neutron Stars, Black Holes and Gravitational Waves. And you can follow me on Twitter at Matthew Bales. Right, so first of all, Sarah's already given the acknowledgement of country, but I'd like to show this image, which was actually created by one of our local Wurundjeri artists, and it depicts gravitational waves propagating throughout the universe. So it's nice to be able to blend a bit of modern science with an ancient culture and their interpretation of it. So let's start off with some of the most influential geniuses behind gravity and how it works, starting with Galileo, who was the first person to really rectify Aristotle's view of gravity, that heavier things don't actually fall faster than lighter things. Johannes Kepler, who used modern observations of his day to understand the motion of the planets around the sun. Isaac Newton, who during a pandemic actually developed the universal law of gravitation as well as differential interval calculus. And then Albert Einstein, who had these wonderful thought experiments that we're going to be hearing more about later on. So Galileo took a telescope and pointed it at Jupiter and discovered that it had moons. And this really transformed the way we viewed the world. Because up until Galileo, we thought that the Earth was in a special place in the universe and that everything revolved around it. But Galileo saw that the Earth had a moon, but also Jupiter had a moon, and you should be able to see the moons of Jupiter going around there. And he realized that maybe it was the sun that was different and that we went around the sun instead of the other way around. Kepler teamed up with Tycho Brahe, who was a leading observer of the time. They didn't use telescopes in the same way that happened later on, but they did have observing equipment that could accurately determine positions. And he took the accurate positions of the planets and realized that they fell in these elliptical paths that you can see here. So the planets go around in an ellipse. An ellipse is just a circle seen edge on. And he realized many things about the planets. One was that they traveled faster near the sun than when they were further away. And he also worked out that the speed at which you went around these orbits depended on the semi-major axis to the 3/2 power, which was remarkable given when he was doing this. And he also worked out that equal areas were swept out in equal times and that the paths of the planets were ellipses. And then Newton came along and, using his universal law of gravitation, that the force between any two bodies depended on the product of their masses and their separation squared, he managed to show that Kepler's laws were just a natural consequence of mathematics and his own law of gravitation. And so this was quite a advance at the time, and Newton was the king of gravity for a few hundred years. But then along came Einstein, and Einstein liked to think of the universe in very extreme terms, and he wondered how light traveled throughout the universe and how it knew what speed to go. And he also asked questions about what would happen if gravity became stronger and stronger, and does light fall in a gravitational field or does it propagate? And he came up with a theory of general relativity. And in general relativity, the ultimate form of matter is a black hole. This is when material is compressed to such a high density that the gravity is so strong that light can't escape. And he also postulated that maybe when two stars went past each other, they gave off waves of gravity, and we call those things gravitational waves. So we're used to living in our local universe, and here's the city of Melbourne where I live, and there's a picture I took on a recent ride. And if you measure the speeds that we're used to in our everyday life, I think the fastest I've ever been on my bicycle is 20 meters per second. It's about 70 kilometers an hour. In terms of accelerations, we can accelerate in a motor vehicle, and this is the rate of change of speed. So a Tesla Model 3, which was my lockdown present, can go from 0 to 100 kilometers per hour in 4.4 seconds. And so we can work out what that means in terms of acceleration. It's actually 100 kilometers an hour is 27.8 meters per second. So when you're traveling along at 100 k's an hour on the Hume Highway, for instance, that's 27.8 meters every second. And if you work out that you can get to that speed in 4.4 seconds in one of these cars, then you're getting 6.3 meters per second faster every second, and that's 2/3 of the acceleration due to gravity. So when we're in free fall, if we were to jump off a tall building, and there's a picture of Einstein here falling, he would travel 10 meters per second faster every second. It's actually 9.8, but 10 is good enough for a public lecture at least. There is wind resistance, so you actually end up having what we call a terminal velocity, but if there was no air, you would fall faster by 10 meters per second every second and have a very painful splash in the Yarra here. But in Einstein's universe, the one that he liked to postulate, speeds approach the speed of light, and the speed of light is 300,000 kilometers per second. And if you could get two stars that were incredibly compact traveling around each other, you'd be able to get them up to speeds of, about 20% of the speed of light. If you put a neutron star next to a black hole, and that's what the artist's impression here is from the famous Carl Knox. In the center of this explosion on the right-hand side is something called the Crab pulsar, and it's a neutron star that spins 33 times a second and probably weighs about 500,000 Earth masses. And so in this universe, Newton's laws start to not work so well, and we need an alternative theory of gravity to be able to explain it. So Einstein postulated that maybe the force you feel due to gravity is no different than the force you feel due to acceleration. So if you're in outer space in a lift and you're accelerating at 9.8 meters per second, or you're in a lift that was stationary on the Earth, that would feel very similar. And one of Einstein's pieces of genius was that he postulated that not only would it feel kind of the same, there would be no experiment inside the elevator that you would be able to do if you had a soundless elevator which made no noise. You wouldn't be able to tell whether you were accelerating in outer space or accelerating due to gravity. And so atoms can't tell the difference, and indeed light can't tell the difference if these two accelerations are happening. And so this had some interesting consequences. He further postulated that if you were in free fall, so you're in an elevator that was just falling towards the Earth, maybe it's got a bit of what we call tangential velocity, so it's going to miss it, you would feel no forces. So you wouldn't feel the acceleration due to gravity, you would just feel like you were falling. And that you would have exactly the same feel if you were just floating in outer space. And so he came up with something called the equivalence principle. And it has a lot of interesting consequences, because if you were holding up two mirrors and light was bouncing between the two mirrors and you were falling, the light would actually be traveling in a curved path. Similarly, in outer space, if you had two mirrors and light bouncing between the two mirrors, the trajectory would be exactly the same from your perspective. And so you can't tell whether you're falling in gravity or just stationary in outer space, according to this postulate of Einstein. So Einstein made these postulates, and then he said, well, if all this is true, there should be certain consequences for the universe. And today we're going to learn whether or not those consequences are borne out by observations. So one of the consequences that Einstein had is that if he's right, light should bend due to gravity, and it wouldn't fall very dramatically. This is probably wildly exaggerated, unless it was a black hole, but light should bend in a gravitational field as it passes a massive object. Another thing which is very surprising is that Einstein showed that the rate at which a clock ticks should depend on how far away it is from a gravitational field. So if you're way out at infinity, your clock ticks at the right rate. If you're near it, it slows down, but so does your brain. So when you're looking at it, it looks as though it's just ticking normally. And this is what some people call the twin paradox. So Einstein ages much faster away from gravity than he does near it. Unfortunately, the gravity on the Earth is not very extreme, so the rate of change of ticking is almost imperceptible to us as humans. But if this was like a black hole, then somebody looking at your clock would think that it had almost frozen. And so the Russians actually call black holes frozen stars because time near them stops ticking altogether. So another consequence is that space should be compressed near bodies. So if you had a bunch of measuring rods, and this is a grid here, the space between the grid lines should get shorter. A ruler will shrink near a massive body. And this should happen both on the surface of the Earth, but also near the surface of what we might term a black hole. We'll learn a little bit more about that in a second. And so he came up with this idea that if you could compress a body into small enough being, it would become a black hole, and the gravity would be so strong that light couldn't escape. And he derived the equation for the radius of a black hole for something of a given mass. And there's not going to be too many equations in this lecture, but this is one of them. So you can take Newton's gravitational constant and the speed of light squared. And if you compute what this figure is for the Earth, you find that the Earth would have to have a radius of about 1 centimetre in order for it to become a black hole. And so you can imagine that trying to compress the entire Earth into something that's only this big is very difficult indeed. One other consequence is that as the mass gets bigger, the radius is proportional. So if you go to the mass of the Sun, it would become a black hole if the radius was 3 kilometers. If you go to something that's 100 times bigger more massive than the Sun, it would be 300 kilometers. So the density required to become a black hole keeps going down as you get bigger and bigger objects. So these black holes would be kind of magical if they existed. You put a clock near them, it would stop ticking. If light from near the surface of the black hole escaped, it would have to fight the gravitational field, and it would change from maybe a blue color to red as it lost its energy. Light, when it went past the black hole, would bend in an extreme way, and you'd be able to sort of see around corners. And the measuring rods would go from, maybe 1 meter here to kind of microns as they got nearer to the black hole. But do these things actually exist? And how on earth could you make one if you had to compress the Earth into something that's only 2 centimeters across? Another thing that Einstein postulated was that if gravity was anything like electromagnetism is the study of light. When an electron goes past a proton, it gets accelerated as it goes by, and it loses energy and gives off a photon. And the photon is just normal light, like a radio wave or a optical wave or even a gamma ray if they get close enough, they're going fast enough. And we call this Bremsstrahlung. The Germans invented this term when they were an intellectual powerhouse near the turn of the 19th century. So here we have a photon being emitted, and Einstein thought if there's anything similar about the universe between electromagnetism and gravity, that when two massive bodies go past each other, maybe they'll give off a gravitational wave. And the nature of gravitational waves is a little bit different than electromagnetic waves. They actually cause material to be stretched and squashed as they propagate out. And you can work out the amplitude of a gravitational wave, or the degree at which it should stretch something. And unfortunately, it's got this c squared and distance and velocity and divided by the speed of light here. And so this ends up being incredibly tiny. So if I could get two black holes and smash them together 1 billion light years away, the Earth would change its size by 1 part in 10 to the 21, which isn't very big. So Einstein thought when he postulated all this that they'd never be detected because they're such an incredibly small perturbation on the universe, even if you get black holes which didn't even exist when Einstein was doing these theories. So if you ever get two stars going around each other, they will actually continuously radiate gravitational waves, and these gravitational waves will take away energy, and that energy has to come from somewhere, and it can't come from nowhere. It actually comes from the orbit, and the distance between the two stars actually starts to shrink, and you end up with them going faster and faster, and the gravitational wave amplitude gets bigger and bigger. They take away more and more energy, and then the two stars actually coalesce, and you just end up with a single star in the middle. And we call this a chirp. So the frequency of the radiation starts off quite slow, and as they get closer and closer, as they're giving off energy, they eventually go around each other so quickly that they give off a burst of gravitational waves which travels throughout the universe. So was general relativity a correct theory? It was first put forward in 2015. And at the time, there was a mystery that if you studied the orbit of Mercury, although it was an elliptical orbit, every trajectory was slightly different. It was called, doing what we call precessing, not by very much. In fact, every year, the angle that the closest approach to the sun is changes by an incredible 1/1000th of a degree. And that sounds like maybe you just made a wrong measurement, but in fact, this has been measured very, very accurately. It was a great mystery around the turn of the century as to what was causing this. And this partly comes about because of this compression of time near the sun. It's also in part because the speed of gravity is actually the speed of light. So an object doesn't see things instantaneously as Newton had postulated. So if I move, my gravity propagates throughout the universe, but it only goes out at the speed of light. Another test that you could do to see if Einstein was right, to see if light really does curve when it goes past a body. And you could write down an equation which said how much the angle should deflect if a star goes past the sun. And it depends on how close it gets to the sun and how heavy the sun is. And so this angular prediction was made, and during an eclipse, I think it was in 1919, a famous astronomer called Eddington took photos of stars near the edge of the solar corona and saw that they had changed their apparent position, and the amount they changed by was in exact agreement with Einstein, to about a 10% accuracy. It took many years to do other tests of general relativity to see if it was correct, because for most of astronomy it was completely irrelevant. One of these ones was that clocks should tick more rapidly when they're away from the Earth than when they're on the Earth. And so these two physicists bought a series of airline tickets, and they took an atomic clock with them, and they booked a seat under the name of Mr. Clock. And this was an atomic clock that they flew around the world. I think they went east all the way around the world and then stopped and went west, and they compared the clocks with clocks on the ground, and indeed saw that they had ticked more slowly when they, more rapidly when they were away from the Earth at altitude than they were on the ground. And this was actually one of the cheapest experiments ever performed on gravity. I think it only cost about $8,000. The Gravity Probe B experiment that the Americans mounted a few years ago was $500 million US. So how big are things in space, and can we actually build black holes? So if you think about the Earth is 40,000 kilometers in circumference. And so I'm not 40,000 kilometers high, but the Earth here is about 6,380 kilometers in radius, And in fact, the meter was defined so that there would be 40 million meters for the circumference, or 10 million meters from the North Pole to the equator. So that was how the Earth's diameter was defined. So it's not a surprise that there's 40 million meters exactly around the Earth, because that's how you define the meter. How about Jupiter? How big is that? Well, Jupiter, I'll just get out of the way here, is about 300 Earth masses. It's not as dense as the Earth. It's probably only about 2 grams per cubic centimeter. The Earth over here is more like, oops, sorry. The Earth here is more like 6 grams per cc. And Jupiter is made mainly of hydrogen and helium. And the helium is actually sinking towards the core of Jupiter, and it causes it to give off more heat than it receives from the sun. But how big is Jupiter compared to the sun? Well, it's a bit of a surprise, but here is the sun, and this is me over here still. And we can hardly see the Earth, which is way back here. There's the Earth over there, and there's Jupiter, and there's the sun. So you can actually fit 1 million Earths inside the sun. It weighs about 300,000 Earth masses, and it's not quite as dense, and it's being held up partly by radiation pressure. So it's giving off so much light that's helping keep the sun at its current diameter. But the sun is not actually a very big star in the universe. There's plenty of stars that are 10 times bigger, and there's even some very rare ones that are 100 times bigger. And so let's have a look at one of them now. I'm still over here. I don't know if you can see me. I'm waving behind the sun. But there is a blue supergiant, and this one is only 10 times the mass of the sun. But it gives off so much energy, it actually gives off 10,000 times as much light every second as the sun does. So it lives its life very quickly. It soon runs out of fuel because it's burning it so rapidly. And in the core of these stars, there's actually a massive chemical factory going on, and it's converting hydrogen to helium and helium to carbon. And then when it gets to iron, a core of iron builds up in the center of this star. The pressure gets bigger and bigger, and eventually the poor old atoms in the core of the star can no longer withstand the amazing pressure in the core, and the protons and electrons are combined together to form neutrons, and the interatomic spacing or repelling forces in the middle evaporate, and the star collapses and it forms what we call a neutron star. So how does that actually work? So this is what's called the periodic table. This is the number of protons in each atom, and it's arranged in a way that helps chemists, and I'm not a chemist and I don't particularly find chemistry very interesting, but there is some parts of chemistry that astronomers are very interested in, and that's how the elements are created. So we think the universe started in a massive fireball about 13.6 billion years ago, and it was so hot that there weren't any atoms at all. It was just energy. But eventually, the universe expanded, which made it cool, and it was possible for it to be no longer so hot that we couldn't create protons and electrons. And the simplest atom is just a proton with an electron around it. We call that a hydrogen atom. An element with 2 protons in the nucleus and 2 neutrons is called helium. Lithium has 3 protons, beryllium 4. And atoms that are in these columns tend to behave the same way. So after the Big Bang, all we had was hydrogen, helium, and lithium. Everything else wasn't created until stars came along. And in the core of that star, which I just showed you, there's this massive chemical factory. And it's smashing hydrogens together to form helium, heliums together to form carbon. And it keeps going until it gets to iron, Fe here. Fe is the chemical symbol for iron. It has 26 protons in the nucleus, and this element has the property that if you try and add another helium atom to it, it actually takes energy to do it. It doesn't release energy. And so you end up getting a whole lot of materials around this periodic, or around this atomic number, and these other elements are not yet in existence. But when the star explodes at the end of its life, and this happens to stars bigger than about 10 times the mass of our sun, you create a lot of other elements. And so we can see how this works. Here's a simple hydrogen atom. It's just a proton. You smash enough of them together, you can make a helium atom. You can put 3 helium atoms together, you can get a carbon atom. You keep on going all the way to iron. And then this is where the chemical evolution stops in the core of the star. But how far apart are these iron atoms? So if you have 2 iron atoms, they have a diameter which is such that if they were the size of a ping pong ball, the nearest helium atom, the nearest iron atom would be 1 kilometre away. So if you can imagine, these are the cores of nuclei. The space between them is about 1 kilometre if they're 40 millimetres apart. These are ping pong balls. And the reason they don't get any closer is because there's a sea of electrons that are keeping them apart. So the electrons are repelling each other, and that keeps these things apart. But at the end of the star's life, the pressure builds up so much that these poor electrons can no longer escape the protons. They get absorbed in the nucleus, they turn the protons into neutrons, and then there's no longer the same interatomic repulsion factor, and that makes even the pressure even greater. And before you know it, all the electrons have been absorbed by the nucleus, and the gravitational force between these things crushes the star and it sends out a huge shock wave, and you end up with a neutron star. So neutron stars were just a conjecture for many, many years. They were first proposed shortly after the neutron was discovered in the 1930s. And people said, wow, if you put enough neutrons together, maybe you could make a star of them. But nobody had any evidence that they actually existed. Radio telescopes had a lot to do with this story, and this is the Parkes radio telescope. And the Parkes radio telescope is one of my favorites. I did my PhD using it. And it's actually a bit bigger than shown here. So it's actually 64 meters across. It's in a parabolic shape, so it focuses radio waves that bounce off this parabolic shape at the focus cabin. I've been actually up to the focus cabin in the days when occupational health and safety wasn't what it is today. And there used to actually be an unofficial title for who could get from the ground floor to the focus cabin in the shortest possible time. And a guy called Harry Fagg was the champion. He used to run down the ladders and run up them. He was incredibly fit. Anyway, the Parkes radio telescope focuses radio waves, and if you point in the heavens, you actually see some very interesting signals coming. And that was done by a woman called Jocelyn Bell. And this is a photo of her in the 1960s. And for her PhD, she was trying to study how radio sources behind the sun would change rapidly. Would they twinkle? So she was studying the twinkling of stars in the solar corona and what we call the ecliptic. Anyway, she noticed that every day there was what she called a little bit of scruff on a chart recorder. She didn't have computers at the time to record her data. And so they cranked up the speed of the chart recorder. And then one night, about 19 hours and 20 minutes after Aries went overhead, they saw these little pulses on the chart. It may not look very interesting, but you'll notice that they're quasi-regularly spaced. And these are actually bursts of radio emission from a neutron star that is beaming towards the Earth. And once every rotation period, it actually shines a light at us. So let's have a look at a virtual pulsar. Whoa, what happened there? Whoa, that's a bit of a bug. Anyway, we'll see if we can rebuild him. Right, so this is supposed to be a neutron star, but the beam has gone a little bit funny on me, which I hope it's not going to wreck the rest of the talk. So this thing at the center, it's a little bit disturbing to look at actually, is supposed to be a neutron star, and it's supposed to have these two beautiful beams that are shining and beaming light out. They've turned purple and become quite ugly actually. So a neutron star is about 500,000 Earth masses. I'm just going to go off that because it's making my head hurt. And it is only about 20 kilometers in diameter. And it has an intense magnetic field. And the magnetic field causes an enormous voltage across the polar cap. And every time the neutron star rotates past the Earth, your radio telescope gets a beam of emission. And these are three pulsars that we've been observing recently at the Meerkat telescope in South Africa. And this shows the power of the radio pulse we receive from this star as a function of what's called its pulse phase. So once every rotation, it has this strange pattern with a little spike and a little bump. This pulsar here next to it just has a broad kind of boring pulse. And the one on the right here has this nice kind of narrow pulse. Now, you may not be able to read it, but this pulsar here is called 1811-24. It's 24 degrees south of the equator, but it rotates every 2.661 milliseconds. This one here rotates every 4.4 milliseconds, and this one is relatively slow, rotating every 33 milliseconds. So this pulsar, this neutron star, which is 20 kilometers in diameter, manages to rotate about 33 times a second. This one rotates over 200 times a second. And this one here, almost 250 times a second. So these neutron stars can really spin incredibly quickly. So how does that come about? Well, often the neutron stars or massive stars are born in pairs, and they orbit what's called a common center of mass. So they create a trail, and the size of their orbit depends inversely on their mass. So if they're very heavy, they have a small orbit. If they're very big, if they're very big, they have a small orbit, and if they're very light, they have a large orbit. So in this system here, there's two stars. One of them is swelled up to become a giant, and it's transferred matter onto its companion. Eventually, one of the stars reaches the end of its life, and it blows up to leave behind a neutron star. The neutron star, this is a much better view of one than our previous aborted attempt. The neutron star goes around in an elliptic orbit, just the same way that Kepler had explained the planets move. So stars move in, have the same laws of physics applying as planets around the solar system. And they go around in these elliptical paths, and the neutron star is giving off this beam of radiation. And every time that beam goes past our radio telescope, we get a flash of light. So we can kind of fly in here and see what's going on. Depending on how the system is oriented in space, we either see it edge on like this, or more face on. It's statistically more likely that we'll see a star edge on than face on, but we do have some that are reasonably face on. And then eventually the companion star runs out of fuel and it swells up to become a red giant. And when it does that, it transfers matter. When the matter wants to fall onto the neutron star surface, the neutron star kind of gets out of the way, and you get the creation of something called an accretion disk. Now, if we look at this system relatively edge on, you'll see that it's quite a thin disk of material, and the material rubs against itself, but it's traveling very rapidly because it's going around a neutron star. So the disk gives off a whole lot of X-rays because it gets so hot, it can get up to 1,000,000 degrees. And if you actually grab an X-ray telescope and point it at the heavens, you don't see anything because of the atmosphere. But if you put one above the atmosphere, you see there's dozens of these things in our galaxy, which are ripping material off companions, and it's falling towards the neutron star surface. So if we have a look at this thing a little bit more face on, you'll see that the material, as it gets closer to the neutron star, is traveling more rapidly, and that makes it hotter. So the inner part of the accretion disk gets very fast. The outer part is relatively cool. So the light we get is more like on the X-ray part of the spectrum in the inner part of the disk than in the outer part. And eventually the material falls onto the neutron star surface, and it makes the neutron star spin more and more rapidly, and it gets spun up until the neutron star is rotating almost 1,000 times a second. And we call that a millisecond pulsar. So it's kind of amazing. These neutron stars, they're 500,000 times the mass of the Earth. They're only 20 kilometers across. In fact, a teaspoon of one of these stars would weigh as much as all of humanity. So just 1 cubic centimeter of neutron star would weigh as much as every human on Earth put together. Anyway, eventually the material stops being transferred and the companion star blows up. The two stars go into a little tight orbit just prior to the explosion, and you end up with 2 neutron stars in an elliptical orbit around each other. But instead of taking like a year or more to go around each other, these systems can be in very tight orbits. And in fact, the tightest one we know about has an orbit of only about 90 minutes. So you've got 2 stars traveling around each other at several hundred kilometers per second. And Einstein's laws need to be used in order to explain these systems. So the stars are traveling so rapidly that they're over 0.1% of the speed of light, and the elliptical path that they're traveling in actually precesses at a very rapid rate. So instead of being 1,000th of a degree per year like Mercury going around the sun, we have one system that actually changes the orientation of the ellipse by over 20 degrees a year. The other thing that happens is that when the 2 neutron stars are near each other, they're deeper in their gravitational pull, and time goes slower because the gravitational field is bigger. So when you discover one of these systems and you observe the pulsar, it appears to tick more slowly when it's near a companion than when it's further away. And then the other thing these things are doing is they're giving off gravitational waves. And so because of their high speeds and high masses, the amount of energy going into gravitational waves is actually significant, and it causes the orbit to shrink. And although the shrinkage is not very much, and you can work it out, it's actually about 3 millimeters per orbit, which sounds like, who cares? If you wait long enough, these 2 neutron stars will eventually get into a hyper-relativistic orbit, and they'll give off a burst of gravitational waves, and they'll get so near each other that they'll actually be traveling at 20% of the speed of light. They'll tear each other apart, and there should be a burst of gravitational waves sent throughout the universe, as well as a special type of explosion called a kilonova, which should light up in the optical. And indeed, a series of gamma rays should be given off in what we call a gamma ray burst. So that's all very well, but how do we explore the universe with these pulsars? So this is what's called the magnetic field period diagram, and every known pulsar is on this diagram. And you can see that the pulsars are born in these explosions. They're rotating about 50 times a second. They have a high magnetic field, and they quickly lose a lot of energy because the magnetic field is so strong, and magnets don't actually like rotating rapidly, especially not 50 times a second. They give off something called magnetic dipole radiation, and they move across this diagram until they're only rotating about once a second, and then they die. But if they're lucky and they have a companion star, they can be recycled by the transmission of material to the neutron star and spin faster and faster and faster, and it causes them to get reborn as pulsars. If the star is very massive that's donating the material to it, it blows up quickly and the neutron star ends up here. If it's of lower mass, it takes a lot longer to transfer the material, and it can spin way down to 1,000 times a second. So here is a very special system that was discovered in 1974 by a guy called Joe Taylor and his graduate student Russell Holtz. And this system is 2 neutron stars, and they travel around each other every 7 3/4 hours. They have an orbital eccentricity of 0.6, so that helps you understand how elliptical the path is and how close they get and how far away they are. And Holtz and Taylor discovered that this system had its elliptical orbit changing its orientation by 4 degrees a year. They also found that the 2 neutron stars ticked more slowly when they were near each other. And a friend of mine, Joel Weisberg, as a postdoc at Princeton, studied this system in great detail and showed that you could use the rate at which the clock was ticking between the extreme parts of the orbit and the speed at which it was processing to completely determine the masses of the 2 stars. And in fact, they could determine the mass of the stars to an accuracy of about better than 0.1%. This means they could work out how much it would shrink, and indeed it was 3.1 millimeters per orbit. So they decided to keep monitoring this system for decades if it meant they could confirm that gravitational waves were giving off. And using the Arecibo telescope, which you can see on the right here, this shows the radial velocity of the pulsar as it travels around its orbit from the Discovery paper. This is a study of the system after many years, and they'd worked out the mass of the pulsar and its companion, and they predicted the rate at which the orbit should be shrinking. And this was the measurement of that, and they showed that all of these lines intersected at a common point, and the system was indeed giving off gravitational waves at the exact rate at which Einstein had predicted. That's rather a handy thing to do if you're an astronomer, because in 1993 they won the Nobel Prize. So they predicted how much earlier the neutron star should get back to the point of closest approach every orbit, and they made measurements of it every year. And then in 1993 they won the Nobel Prize, and they stopped measuring. And then a few years later they came back and started measuring again. And so this showed that gravitational waves existed because they took away energy at the exact rate that Einstein had said. But it wasn't really a detection of gravitational waves, it was just showing that they must exist. So they went off to Congress and said, we want to build something called LIGO in order to discover neutron stars in the universe that not only are going around each other every 7 hours, we want to get ones that are going around each other 1,000 times every second and giving off a huge burst of gravitational waves. And so this was funded, and the idea was that you would get 2 stars, one would blow up, and again I've got a bit of a graphics problem here, I have to talk to Mark. The other would. Then eventually these 2 stars would go around each other so quickly, and I apologize for the jets being the wrong color, but they would go around each other so rapidly that they would complete 4,000 orbits in the last couple of minutes and give off a huge burst of gravitational waves that would propagate throughout the universe, and we would get something called a kilonova explosion. and leave behind maybe a black hole. But it took over 20 years to build LIGO, and in the meantime, pulsar astronomers like myself were discovering other systems. This is a system called 1909-3744. I'm quite fond of it. When we look at this system, it is actually remarkably edge-on. So when we observe this system with our telescope, we're seeing it at an angle like this. And what happens is that when the white dwarf, which is its companion star, I haven't really explained what a white dwarf is, but it's the remnant of a star that doesn't explode, is not big enough. When the light is traveling past the white dwarf, we've got more measuring rods fitting in, and so we actually get a delay. So I'm going to show you some experimental data that shows how well we can measure the system. So it is indeed going in an elliptical orbit, and we can describe an ellipse by how big the semi-major axis and semi-minor axis is. A circle has A equal to B. An elliptical orbit with an eccentricity of, say, 0.8 would have A about twice that of B. But in this system, the orbit is 569,397 kilometers, and the difference between A and B is only 3.7 microns. That's 3.7 millionths of a meter. So this system is incredibly circular. In fact, we use when the pulse arrives at our telescope to effectively map the orbit. And here you can see when the signal from the pulsar arrives compared to when it should for a perfectly circular orbit. And you can see that it's delayed and then it comes earlier. And this delay is caused by the fact that the light from the pulsar has to travel past the white dwarf companion. And then this is the difference between Einstein's prediction of what this shape should be and the data. And you can see it's beautifully clustered around 0. Okay, let's move on to LIGO. How am I doing for time, Sarah?
You're doing good. I would say maybe another 5-10 minutes. And in this quick intermission by me, if anyone has any questions, you're welcome to email swin@swin.edu.au. I've emailed everyone who signed up to request your questions. Please bombard us, because unfortunately the Teams question function is not having it. It's retired for the Friday. But yeah, about 10 minutes. Is that okay, Matthew?
Yeah, fine.
Brilliant.
Okay, so this is an aerial view of one of the 2 LIGO observatories. So LIGO is the Laser Interferometer for Gravitational Wave Observations, or LIGO for short. It costs about $500 million, and it has 2 facilities, one on either side of the US. And in the core here, there's a very powerful laser beam. You can sort of think of it as a James Bond style laser. And the laser is fired, and there's a splitter which sends half of the light down one arm of this vacuum tube, the other half down this side. It bounces off a mirror, and then it travels back again. And it's actually 4 kilometers to get to the other mirror. So you've got to aim the laser beam very precisely. It's remarkable to me that it actually works. It comes back and then it bounces to and fro, and there's a one-way mirror here, which lets through a little bit of the light, but mainly sends it back. So in the cavity, we have a huge amount of light bouncing to and fro with a little bit of light leaking through. And if a gravitational wave compresses the Earth, it'll squeeze one arm more than the other. And when the light is recombined, it's actually set up so there's exactly a half a wavelength difference between the 2 arms. And so if there's no gravitational waves and no noise, you would just get 0 light. But as soon as a gravitational wave goes past the system, it should squish one arm more than the other and cause what we call the interference pattern to start receiving light, because the light will no longer be exactly half a wavelength apart and will no longer be cancelling each other out. And so the idea is you fire this laser beam down, and then you wait for 2 neutron stars somewhere in the universe to merge, and then you should see a little burst of light, and it should have a very characteristic shape, which would enable us to say we've detected gravitational waves. So this was the idea. And so back in 2015, they were testing it, and they were about to start a few-month observing run, and they saw an amazing signal. This is me at the facility on the left here. These are the huge vacuum tubes where the laser beams are and the beam splitters and all of the signal recycling cavities and all these amazingly technical things are present. So this was me at a visit to LIGO a couple of years ago. I'm on one of their advisory boards. This is a picture which gives you an idea of the vacuum tubes, and it's about to go down the vacuum tunnel. But there's various instruments. They have to be in a vacuum because you can't have the light being absorbed by the atmosphere. It's one of the biggest vacuum tubes in the world. And this is an idea, a simplified idea of how it works. So you have a laser beam here, you fire it, gets split, it goes down to 2 mirrors, they come back, and they're exactly half a wavelength apart, so you shouldn't see any light coming through here, unless you have 2 black holes or neutron stars merging, causing these arm lengths to change, and then you should see light. So that was the kind of theory. And indeed, as they were doing their commissioning, they had this remarkable signal come through. So you can see it starts off with a sort of a slow period. It gets faster and faster and bigger in amplitude, and then it goes away. And so this was the signal in the Hanford detector, which is where my photos were from. And then the Livingston detector did exactly the same pattern, but shifted by, I think it was 6 or 8 milliseconds. And that's about the time a gravitational wave takes to travel between these 2 detectors. And then this is the model of what we think occurred without the kind of noise. And you can work out from the speed at which this frequency is changing and the amplitude what kind of stars must have collided in order to result in this. So if you do the maths, you find out that 2 30 solar mass black holes collided about 1 billion light years away, and they caused the Earth to shake. And the amplitude here, the change in the distance of the arms, was a massive 10 to the minus 21, or 1 part in 10 to the 21, or 1/10,000th of the width of a proton. And so kind of a remarkable feat that you can do that. You do it by having sort of like a megawatt of laser power in the cavity. And so these are the 2 signals, and that's them over shifted and lined up. And so you can see that we indeed were discovering black holes merging in the universe, which is kind of incredible. So this is the idea that you have 2 black holes. And the thing about black holes is they don't give off any light at all. So it's impossible to know the population of black holes in the universe unless they do something interesting, like collide. So if you have 2 30 solar mass black holes, over the course of 1 billion years or so, the orbit decays to the point where they get so close that they're almost touching, and they give off this burst of gravitational waves in the last 10 orbits or so that is detectable by our detectors. So this was a remarkable discovery, and it led to the Nobel Prize for the founders of the project. But OzGrav, our Centre of Excellence, was engaged in many aspects of this research, and I think there were over 1,000 people on the discovery publication. And we did things like get lock for the lasers and stop the thing wobbling, make sure the mirrors were clean, and do some of the testing of the detector system. So we're quite proud to have been involved in this discovery. A more remarkable thing in some ways happened 2 years later. In fact, on the 17th of August 2017, there was a gravitational wave detected, but this time, instead of just seeing the last few orbits of two black holes, we saw two neutron stars collide. And what we have is time on the x-axis down here and the speed of the gravitational, or the frequency of the gravitational wave on the y-axis. And you can see this beautiful trail. And this is actually the frequency of the gravitational wave as a function of time. And it represents the last 4,000 orbits of two neutron stars as they ripped each other apart. And then 1.5 seconds after they merged, there was a burst of gamma rays hit the Earth. And indeed, a whole lot of optical telescopes pointed at the direction that these signals from. There was kind of a big error box from the gravitational waves and the gamma rays. And so they looked at every single galaxy in this particular part of the sky to see if they could see anything interesting. So we had the two neutron stars. They gave off their gravitational waves, and for about the last 4,000 orbits, the frequency of the gravitational wave was just suitable for our detector to be able to see it, and we saw them rip each other apart. Where they were in the screen, in the sky, was actually not super precisely known. So there was this error box on the sky. I might actually turn myself off because I'm not sure I'm helping. So this sphere represents the celestial sphere. We're in the middle of it. And we knew that the gravitational wave had come somewhere from this stripe. And so they overlaid that with the error box from the gamma ray telescope and concluded it must come from a patch of the sky that was about 20 or 30 square degrees. And we were effectively surveying the nearest million galaxies at that time. So this is 40,000 of the brighter galaxies that we know about in the local volume in the southern hemisphere. I haven't shown the northern hemisphere ones, it gets a bit confusing. But the signal could have come from any one of these galaxies, but we knew roughly the distance to it and whereabouts in the sky it was. So we can fly in, and it was actually from this green dot here. This galaxy here was the galaxy in question, and when we took a photo of it with the Hubble Space Telescope, you could see it was an elliptical galaxy with this brand new star here where the arrow is, and that was what we call the kilonova. And the kilonova is about 1,000 times brighter than a regular nova in our own galaxy, but much less bright than what we would call a supernova. So this was the neutrons, stars ripping each other apart and sending a cascade of neutrons out. It formed a bunch of atoms, and it created a whole lot of the heavier elements than iron that we see in the universe. So what were the scientific outcomes of this discovery? Well, it was the first detection of a kilonova, two neutron stars ripping each other apart. That was kind of fun. It's how elements like gold are made. The neutrons can seed iron atoms and cause them to get more protons in the nucleus. So this is how you make gold that's in your wedding rings. We found out that the speed of gravitational waves and the speed of light was almost exactly the same. Even though the system was over 100 million light years away, the two signals arrived within a few seconds of each other. And we think this is because the gamma rays take a while to escape. And we could measure the amplitude of the gravitational wave, and that told us how far away the system was, and we knew the redshift of the galaxy, or how fast it's receding from the Earth. And so this gave a measurement of the age of the universe in a very independent way. And finally, we discovered that neutron star mergers did in fact lead to gamma ray bursts. Gamma ray, if you look at the sky a few times a day, there's a burst of gamma rays, and it was always a great mystery as to what was causing what's called the short gamma ray bursts. There's been many other events detected by LIGO since. I think we're up to 50 or 60 events, and here's two of the most massive neutron star or black holes ever discovered. These created a black hole which was 142 solar masses after the merger. So if you actually work out what the mass of all of the systems that we've watched merge, there's a bunch of these black holes that we never really knew about their existence until LIGO turned on. And then there's the neutron stars that are sometimes merging with black holes and sometimes merging with each other, which are much lighter. So LIGO has taught us a lot about gravity in the universe. It's confirmed many of Einstein's theories, and it's beautiful to see how the combination of the different wavelengths from Jocelyn Bell's discovery of pulsars with neutron stars has led to the prediction that these things should exist in the universe, and then LIGO's come along and measured them, and not only discovered merging neutron stars, but discovered these merging black holes that we really had no way of knowing even existed. So I might stop there. Sarah, I'll just go through some of the other slides and get to my final slide, which I had a lot more material, but I think we don't have time for it. So let's just.
Maybe we'll have to have a second. Matthew last section.
Yeah, so LIGO is about to have its third observing run next year. It'll see further into the universe, and OzGrav is part of the effort to make it bigger and better. We'll then have what we call O4 in about, what's that, 2023, and we'll keep seeing further and further into the universe as we up the laser power. And the aim is to make it about 3 times better, which is about 27 times as much of the universe as we can currently see. And then ultimately to build what's called the 3G detectors. These are ones that are going to have 10 times the arm length and much more powerful lasers. And we've written a science case and the technical challenges that are involved in making these detectors, but these could almost detect every merger in the universe. So thanks very much for listening. I'm sorry we couldn't be there in person. If you have any questions, please either email them to Sarah or tweet them or try and use the chat. But we used to do fundraisers when we were in person many years ago, and if you would like to donate as a thank you, we're raising money for kids' cancer this month, and if you go to this URL or use this QR code, you can sponsor me for as little or as much as you like to fight the kids' cancer battle. So thanks very much, and I'll get Sarah to read out any questions that she may have had.
Awesome. Thank you so much, Matt. That was brilliant. So we do have a couple questions. One of them, which I think is near and dear to your heart, is, are we trying to get our very own Australian gravitational wave detector? How likely is it to go ahead, and how would it be different to other gravitational wave detectors?
Yeah, that's a very good question. So there's not a lot of point in building an identical gravitational wave detector to the ones that are already in existence, because we all see the same universe. They all stretch and squeeze. The orientation of the detector has a minor change if you're pointing in a different way, but building a detector which is exactly the same as LIGO wouldn't actually make a lot of sense from a sort of science per unit dollar. At OzGrav, we've had an idea that maybe if you turn the power up a lot and didn't worry about low frequency gravitational waves, we could actually discover many more neutron star mergers. So we do have a proposal, it's more of a concept than a proposal, to can we do the type of research that will show whether we're capable of upping the laser power by, a factor of 5 or 10. This would make us be able to see further out, but would also give us information about the neutron stars in their last few cycles, which is where you learn about how nuclear matter is put together. So we'd love to be able to do that, but we'd also like to be part of the third generation detectors that we see as a global effort. It's actually very handy to have more than one detector because it means you can triangulate on the sky where the source came from. So we'd love to either build our own high frequency detector or be part of a worldwide collaboration to have maybe one detector in America, one in Europe and one in Australia. And we'd like to focus on that high power end.
Awesome, thank you. Another question about gravitational waves that we got is, I'll read it verbatim. So it is, you comment on the changes in gravity, that the changes in gravity are transmitted at the speed of light, but gravity itself is actually omnipresent as an ontological phenomena. Sorry, I cannot pronounce because I'm a little bit dyslexic, so I have trouble reading. So basically gravity doesn't itch, it doesn't move. It's like a property of gravity is not that it moves at a certain rate and doesn't need to travel, right? So I think the question is getting at, why do we see these gravitational waves moving like we would see water moving in like a pond or something like that, when we tend to think of gravity as kind of being a bit static?
Yeah, so certainly when we're on the Earth, we don't feel that gravity changes at all. In fact, gravity does change because of the motion of masses. And gravity also changes because stars travel around each other. So you feel a different gravitational field as stars move past you. If I raise my hands, the mass in my hands is closer to the roof than it used to be, and there's actually an increased gravitational force. So there is a very subtle change in gravity because of the motion of things on the Earth. But on stellar scales, when stars are going around each other, the gravitational field seen from afar is changing in a kind of a dipolar and quadrupolar way. So gravity does actually change, or the effect of gravity is changing as stars go around each other, and that's causing the transmission of these gravitational waves. So it's the change. In fact, the amount of gravitational waves you give off is the third time derivative. So it's not the rate of change of the position or the acceleration. It's actually the acceleration of the acceleration determines how much gravitational power is emitted.
Awesome, great answer. And I think final question we'll wrap up with is, what are you most excited about for future discoveries? So I think in the terms of, you talked a lot about Einstein had very little faith that we were going to be able to detect these gravitational waves, and yet here we are. What do you think will come next in the next 50 years or so? Something that might shock or surprise us?
Look, I'd love to discover something that we're not clever enough to think of. So it would be awesome if there was a new type of star discovered, or that we couldn't explain. I was lucky enough to be part of the discovery of fast radio bursts, which are these weird flashes of radio light. And I think what was so exciting about that was we had absolutely no idea what caused them. I think when you discover something that you haven't thought of, that's much more exciting than something that you know is going to be there. So I would hope that we would discover things that are completely shock us. That would be my most exciting thing. I was very excited to see the neutron star merger because I did my honours degree in 1984, and I was studying the neutron star binary system that eventually won the Nobel Prize for Taylor and Holtz. And I knew that system was going to merge in 300 million years, and I thought, gee, wouldn't it be awesome if you could actually see two neutron stars merge? And as the director of a national gravitational wave center, 30 years later, 33 years later, we saw it. So it took a third of a century, but the thing I studied as an honours student, these two neutron stars, I saw a system like that was 300 million years older, ripping each other apart and creating a new star in the sky. And that to me was a great highlight.
Yeah, absolutely. So thank you so much again, Matthew, for giving such a fantastic lecture, and thank you everyone for attending. We hope you enjoyed it. I will send a follow-up email and include this link if you'd like to donate to the Great Cycle Challenge, and we hope to see you next month. Thank you.
Thanks, everyone. Thanks, Sarah, and thanks to Carl.